So, dear students, you are welcome in this class, and we continue with the topic we started yesterday, methodological interpretation of fertilizer experiments. And the major methodology is to go for response curve fitting and then see the relationship between fertilizer or nutrient and yield. And then we will apply certain economic principles to have the optimum economic dose of the fertilizer. So we started with the references, and yesterday I sent you one book, Soil Fertility Evaluation and Control. So you can read certain topics or certain chapters of your interest in this book. Then I also shared you book by Gomez and Gomez, and you remember what are the learning objectives. And then we have seen different methods of evaluation of soil fertility, critical level, and then this one, different methods for evaluation of soil fertility. And then ultimately fertilizer experiments can tell you the exact relationship between fertilizer and yield, and you need to conduct some experiments and then get some results. Those are observed data, actual data. And then from these, you want to make some predictions because there are many unknown levels of nutrient for which you want to predict the yield. That is why you want to make a representative line that can represent this data well. That line is developed by regression analysis, correlation and regression analysis, and then you apply some economics into it so that you can get the optimum dose. In case of linear relationship, you cannot decide the optimum dose as the returns are constant. So we started with response curves, relationship between input and output, and different types of response curves, their shapes, and then two kind of equations, exponential, polynomials. We are dealing with polynomials where power of the variable are 1, 2, 3, 4, 5, 6. And polynomial of degree 1 is a straight line, y is equal to a plus bx, and so on. And then we discussed the details about the equations. We started with the response curve fitting. So you want to make a representative line, regression line or response curve that can represent your data the best. And what line or which line will represent the data best, where you have distances between observed data and predicted data, and square those distances and make the total. The line which is giving you least sum of square is your best fit. And to get the best fit, for example, if equation is y is equal to a plus bx, then you need to measure or you need to compute the value of a and b so that you get the best fit. So we discussed the method of least square. I tried to explain you with the help of this figure, and some of squares of the distances of errors should be the least, and that line will be the best fit. Residuals are the error, the data which remain unrepresented, which is away from the line, is your residuals. So you can see the data which is above from the line is the distance between that data and the line data is your residual or error. Correlation, we started. What is correlation? Association between two variables. It just give you some idea whether two variables are related or not. If they are not related, the correlation coefficient can be worked out, which may not be significant. If correlation coefficient is significant, then you can say that these two data are genuinely related. Then regression analysis. So we started with regression analysis. It tells the numerical or exactly quantitative relationship between two variables. One is independent variable x and dependent variable y. And then to see it, we need to work out the regression coefficients through regression analysis. We try to explain you dependent and independent variables, some terminology related to correlation, scatter plot, linear correlation coefficient. It is your Pearson product moment correlation coefficient. And then differences in simple and multiple correlation regression analysis. So in this case, it is simple when only one independent variable is influencing one dependent variable. Then it is simple correlation and regression analysis. If more than two variables are involved, say 3 or more, then it becomes your multiple correlation and regression analysis. Now we start with the different 3 types of correlations, just to give you some brief idea. But up to now, if you have any question, you can ask me. Any clarification, any doubt, anything in your mind, it is the time to get it cleared. Don't fear, don't worry. I will not be annoyed if you ask questions. Rather, I will be happy. Are you there? Yeah, Krishna.
Yes, sir.
Are you there? Okay, so that means the things are clear to you, or you are hesitant to ask the question. There will not be your insult if you ask a question. Even if you ask a wrong question, that does not matter. Nobody will laugh. So never fear other people, what others would say if I ask this question. You can seek your doubts, clarification.
Hello, sir.
Yes, Deepak.
Sir, what is the main difference between correlation and regressions?
Okay. Main difference between correlation and regression. See, correlation tells us just the association between two variables, whether two variables are related or not. For example, in general, if your height increases, the weight also increases. So we want to check whether height or weight are related or not. Are they associated or not? So for this, we can see the association and we can check it statistically by working out the correlation coefficient. Correlation coefficient tells us the strength of relationship, whether there is some strength between what level of association is there. That is told by correlation coefficient. On the other hand, regression means the quantitative relationship between two variables. Means if I make 10% change in X, X is your independent variable. What percentage of change will be there in Y variable? If I make a unit change in independent variable, then what unit change is there in dependent variable? So that is numerical relationship. For example, if I say that my height is twice the height of yours, that means my height may be 2x and your height maybe is equal to y. So 2x is equal to y. So this 2 tells us that your height is twice my height. Whatever you means, there is some numerical association between two variables. So this is your regression. Is it okay, Deepak?
Yes, sir.
Amount of change in y associated with unit change in x. Amount of change in y, how much this dependent variable is changing due to unit change in independent variable x. So this is exactly the nature of relationship. Nature of relationship is your regression. Otherwise, if you see the literal meaning, regression meaning is going back, going backward, going backward. Now, to make you further understanding what Deepak has asked, I'm showing you what is the difference between correlation and regression. Take some examples. The bigger they are, the harder they fall. So this is not numerical association. This is just kind of physical or kind of qualitative relationship. The more, the merrier. Easy come, easy go. The better the day, the better the deed. As the twig is bent, so is the tree inclined. So these are some sayings, and which have one part is related to other part. So each saying implies two variable quantities. Magnitude of one is depending on the magnitude of the other. They are called as independent and dependent variable. For example, easy come, easy go. So easy come is your independent variable and easy go is your dependent variable. The more, the merrier. More is your independent and merrier is your dependent variable. So if you want to be happy, you should have more. So here the more is independent variable. As one variable increases, so does the other. So in this case, you are seeing as the left side variable or first variable increases, other also increases. That means it is a positive correlation. So if one variable increases, other variable also increases, that is your positive correlation. So you can see, now you see another case, much haste, little speed. Small pitchers have big ears. The best gift comes in small packages. So you can see there seems to be some negative or inverse correlation. As one is increasing, other is decreasing. So here you get negative correlation. Now you can see in this picture, are you studying some statistical courses in statistics?
Yes, sir. Yes, sir.
So they must be teaching you correlation analysis, positive correlation, negative correlation. So in this picture, you can see on the left side, one is increasing, other is also increasing. So that means it is your positive correlation. Normally on x-axis, we represent independent variable, that is x. On y-axis, we represent dependent variable, that may be yield, growth, or any other parameter. In negative correlation, your one variable is increasing, the other is decreasing. So this is your negative correlation. So what will happen if both the variables are decreasing? What will happen if both the variables are decreasing? Can there be any case where two variables can decrease? What will be the relationship, kind of correlation? Will it be positive, negative, or no correlation when both are decreasing? So that will be a positive correlation. So you can see this case. In this case, on the left side, you get some data, 0, -10, -20, -30, -40. So X is decreasing. And you see Y. Y is also decreasing, 28, 0, -9, -15. And this line, that means your this is your positive correlation. Negative correlation, you are seeing, this is also positive correlation. -5, decreasing, decreasing. Now, there can be a situation where two variables are not related. So in this scatter plot, you can see there is no any trend in this data. So a relationship between two variables for which the points in the corresponding scatter plot do not fall in approximately a straight line. So you cannot draw a straight line here. Non-linearity may occur because there is not a defined relationship between the variables as in the first two figures. So, but in this figure, there is no any kind of relationship. Therefore, it is no correlation. Now, regression, what Deepak asked, you can concentrate now. It is amount of change in one variable associated with a unit change in the other variable. You must remember these lines, these words, if you want to tell the exact meaning of regression. Amount of change in one variable associated with a unit change in the other variable. That is your regression. Correlation refers to the fact that two variables are just related, and closeness of this relationship, how closely they are related. Regression, on the other hand, refers to the nature of relationship. Now you see some examples to explain the regression. A penny saved is a penny earned. A bird in hand is worth 2 in the bush. A stitch in time saves 9. One picture is worth 1,000 words. So you are seeing there is some kind of relationship between two variables. If you take penny as independent variable and penny earned as dependent variable, so one penny is a one penny earned, means here you can see x is equal to y. Here x is equal to y. A bird in the hand is worth 2 in the bush, means 1x is equal to 2y. A stitch in time. So likewise, you can have some kind of relationship. Now you see this I'm sorry, this is x. Example of regression equations and coefficient between independent and dependent variable. Independent variable is, for example, penny saved. Dependent variable is your pennies earned. And regression equation, the relationship y is equal to x. One penny saved, one penny earned. So y is equal to x. So here y is equal to 1 into x. Actually, it is 1 into x. So 1 is your regression coefficient. It is function. If you remember, y is equal to fx. So 1 is your f. Hand birds and birds in bush. So y is equal to 2x. So here regression coefficient is 2. A stitch in time saves 9. Here y is equal to 9x. So y is equal to 9 times of the x. So this 9 is your regression coefficient. Pictures, one picture is 1,000 words. So y is equal to 1,000x. So you can see in the column number 3 of the table, it is regression equation, column number 3. These are equalities of a straight line. Y is equal to a plus b, they represent. The symbol a is called the intercept, since when x has the value of 0, y is equal to a. You will learn in detail what is intercept. When your x is 0, then value of y becomes your a. Hence the line crosses the y-axis at a unit from the origin. When a is 0, the line passes through the origin. If a becomes 0, the line passes through the origin. For when x equals 0, y is also equal to 0. You will learn it. Just have little wait. So now the symbol b is called the slope, since it determines the steepness of the line. So slope, it is actually change in y due to unit change in x, delta y upon delta x. It is easy to see that b is the amount of change in y associated with a unit change in x. So this b in the equation, y is equal to a plus bx. So if you remember, b is your regression coefficient. So it is easy to see that b is the amount of change in y associated with a unit change in x. Therefore, it is logical to call b as the regression coefficient. It is also called as regression coefficient slope. It is also called as slope of the line. It tests the numerical relationship between x and y. If you make a unit change in x, how much change is there in y? And if you progresses, if your levels of input increases, this change will be smaller and smaller and smaller. And sometimes it may fall law of diminishing return. Sometimes it can be a straight line, but sometimes it can be following the law of diminishing return, where the change or the increase in values of y due to changes in x may be smaller. So you will see it. And this is roughly, you can remember that it is almost your marginal return. It is your kind of marginal return. It is similar to marginal return, not exactly marginal return. So now we see the linear relationship in detail. First, we will see linear relationship or curve fitting. Curve fitting for linear data. Data can have two kind of trends or three kind of trends, whether your data from the field may have linear relationship or it may also have curvilinear relationship. So first we will learn linear relationship. The linear relationship between any two variables is linear if the change is constant throughout the whole range under consideration. The graphical representation of a linear relationship is a straight line. I repeated it many times. The functional relationship between a dependent variable y and independent variable x is represented by the equation y is equal to a plus bx. So where a is the intercept, as I told you, a is the value of y when your x is 0. So a is the intercept of the line on the y-axis and b is the linear regression coefficient. You can simply call it regression coefficient or you can put a word linear regression coefficient. Like in case of correlation coefficient, you can also write correlation coefficient or you can also write linear correlation coefficient. It is the slope of the line. B is the slope of the line or the amount of change in y for each unit change in x. So if the intercept of A is 1, suppose the value is 1, means yield is 1, and the linear regression coefficient is 2. The relationship is expressed by y is equal to a plus 2x. Y is equal to a plus 2x with two parameters of the linear relationship, that is a and b specified. Here a is 1 and b is 2. Regression coefficient is supposed assumed to be 2. The value of the dependent variable y corresponding to a given value of the independent variable x within the range of x values considered can be immediately determined. So by this, you can make the predictions. In place of x, you can put value 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you can make predictions for y. So that is the main purpose of having this kind of relationship. When there is more than one independent variable, say k independent variable, the simple linear functional form of equation can be extended to the multiple linear function. So sometimes you can have many independent variable that can affect one dependent variable. Then you can have x1, x2, x3, or bk, xk. This is multiple regression. Now, we go into the details of regression analysis for linear relationship. Regression analysis try to fit a model to one dependent variable based on one or more independent variables. In most cases, there will be error. Error is equivalent to your residuals. The goal is to minimize the errors from the actual data to the regression line. The least squares line minimizes the sum of square of errors. The regression equation or lines helps to predict the values of the dependent variable for a specified value of independent variable. So this is your regression analysis for linear relationship. Simple linear regression analysis means one independent variable and only one dependent variable. So it is method of finding the line of best fit between the dependent variable y and the independent variable x. So as I already told to you that field experiments are conducted and you can record a variety of data including yield. So you can have fertilizer and then yield data. The recorded data are considered as observed values used to fit the regression models or regression equations. These fitted values give a regression equation line that can be used to calculate the expected value, predicted value, or estimated values. But before fitting any relationship between input and output, it must be ascertained that the output due to different levels of input is significant. Means, as I told you yesterday, you need to go for F-test of your data, and then you go for ANOVA, actually, analysis of variance, And if your data is significant, then only you can proceed for correlation and regression analysis. If your data is not significant, if your results of yield due to fertilizer application are non-significant, then you cannot go for correlation and regression analysis. And method of least square is used to compute the, or to make the, to develop the, to fit the linear regression equation. You can call it by different name: to fit it, to make it, to develop it, to estimate the equation, to work out the equation. The main purpose is to compute the equation, to calculate the equation. Once you have calculated or estimated the equation, then you can convert it into form of a line, form of a graph. Now, you see, this is again for your understanding the method of least square. I am explaining you. So on x-axis, you have value of x. On y-axis, you have value of y. And you can see the red colored dots. These dots are your actual data, observed data. And you cannot join these lines of red data. You are not supposed to join these data. Because, for example, you know what is y2 at 40. At 40, you know what is the value of y2. But you do not know what will be the value at 50. You do not know. So then what is the way out? Way out is that you can develop a line that can represent this data the best. And the line which will be the best one should have the sum of square of distances should be the least, should be minimum. That line will give us the best fit. And to work out that line or equation is y is equal to a plus bx. You need to calculate value of a and b. If you estimate the value of a and b, you are able to find the best equation. You are able to fit your data the best. Now you see how to find out the value of a and b. So to find out value of a and b, we will learn it. First thing is how to compute the sum of square of differences and residuals. How to work it out. You have seen in the last case, these are capital Y1, small y1. So small y is represented by computed your expected value or predicted value or value which are on the line. And capital Y2 is your observed data. So in this case, in table, you see first column is X, your input, and Y column is your output, and represented by capital letter, and expected value is small y0. And you can take the differences of these values, y0 minus y0, and square the value. You square the value in the next column, and then make the total of this. This should be minimum. Similarly, you can calculate the residuals in this way. The data from equation can be subtracted from the original data. You will learn it slowly. And then you can work out the values of X. You need these parameters to calculate the value of A and B. To calculate the value of A and B, you need to calculate the mean of X. So this is your data. This is your X, independent variable. You can take the mean of X. Similarly, you have observed data Y. You can take the mean of Y divided by number of pair of observation. Then corrected sum of squares. Xi minus X mean whole square. That is summation X square, small x square. Summation small y square. Yi minus y bar whole square. And corrected sum of square. So these are calculated parameters that you will learn surely. I will teach you how to. And then you can calculate the value of B and A by this relationship. B is equal to summation x5 upon x square. A is equal to y bar minus bx bar. You can put the value of B here. First, you calculated the value of B, and then you can put this value in the equation number 2. You get the equation value of A. And then this I will teach you in the next lecture these kind of ANOVA, analysis of variance. In the next lecture, I will take up one example. Where we will teach. Otherwise, you need to test the linearity of the equation. Now you have find out the equation y is equal to a plus bx. but you need to test this equation, whether this equation is linear or not. You want to know it. So for this, you need to test this equation for linearity, whether equation is linear or not. For that, you need to go for ANOVA test. I will explain you this ANOVA test in the next lecture or next part, sorry. And then you can calculate the value of F calculated, and this can be compared with the table value, and your equation can be declared as significant or not, linear or not. So I will open the next link. This link is going to be over. So welcome back again in this class. Now you can see, as I told you, once you have worked out the equation y is equal to a plus bx, now you want to test this equation, whether it is genuinely a linear equation or not. You need to test it for linearity. So for this, you need to go for, again, for F test, which is your ANOVA, analysis of variance. And in this case, you can see source of variation. So one source is regression. One source of variation is regression, or you can see linear association or regression. Normally, you can say one source is regression and other is residual. Residual is your error. As usual, you get error and then total. So in this case, degrees of freedom, when your you got different degrees of variable in equation. In linear equation, you get power of x as 1. In quadratic equation, you get power of x as 2. In cubic, you get 3. So if your regression is linear, then degree of freedom is always 1. If your regression is quadratic, then degree of freedom is always 2. If your regression is cubic, then degree of freedom for regression is 3. So according to the degree of regression, you can put here degrees of freedom. Degree of variable x. So then total, you know, n minus 1. N is your total number of pair of observation minus n. And then residual, you can easily work out total minus regression. That will be your residual. So n minus 1, it gives you n minus 2. So for error or residual, degree of freedom is n minus 2. Then sum of square. Sum of square, you can work out from the this data. You know this how you can work out. You have value of x. So here input is your x. X, you have value of x, you have value of y, value of this small y. So you can take means of x, means of y, and then you can work out the corrected sum of square against the independent variable and dependent variable x and y by subtracting the means and squaring them. And also you can have corrected sum of square of cross products. So this is the way to get these parameters. And then you can see this sum of square. Sum of square, how to calculate the sum of square. So first sum of square is sum of square due to linearity or sum of square due to regression. You see in summation y square L, you can write is summation y square R also. So sum of square due to regression is equal to summation xy whole square divided by summation x square. So this is how you can calculate the sum of square for regression. Then you need to calculate the sum of square for residual. So this can be calculated by difference method. See the last row for sum of square, total sum of square. So total sum of square is small summation y square. This summation y square is your deviation against y, and you square those values and take the total. It will give you total sum of square. Total sum of square, you can calculate it easily. I will show you in the example how to calculate the total sum of square. And from this total sum of square, if you subtract the regression sum of square, then you get the residual. as you calculated the degrees of freedom, same way you can calculate the sum of square for residual by subtracting subtracting regression sum of square from the total sum of square. So here you can see against the residual, summation y square r is equal to summation y square. This is total sum of square minus regression sum of square or sum of square due to regression. Summation xy whole square divided by summation x square. So this is how you can calculate the sum of squares. Then mean square, as usual. If sum of squares are divided by degrees of freedom, you get mean square. So you can get mean square for regression, mean square for error, you can get, and then mean square for regression is divided by mean square for residual, MSL divided by MSR. So here L is actually mean square due to linearity or mean square due to regression. And then MSR is mean regression due to residual or error. So then you get F calculated, and you also got F table value. F table value at 5% or 1% at 1 and n minus 2 degrees of freedom. At 1 and n minus 2 degrees of freedom. Now my question is, in F ratio, you get 2 degrees of freedom. One is say 1, other is n minus 2. So which one is vertical and which one is horizontal? When you see the F table, so which one is at first, which one will you see? 1 or n minus 2, and to which direction these value mean? Yeah. Anybody? Yeah, Shubhjit.
Yes, sir.
You get 2 degrees of freedom, 1 and n minus 2. You have F table. In F table, the level of significance may be 5% or 1%. So of course, there are 2 degrees of freedom, and you want to find out F table value. So one is your horizontal line, other is your vertical line. So one kind of degrees of freedom on the vertical side, one on horizontal side. So which to see first?
Sorry, sir, I don't know.
Don't know. Anyone else who knows it? Krishna, your mic is on, I think. So actually one is to be seen in horizontal line, and n minus 2 is to be seen in vertical lines. And if your F calculated is greater than F table, that means it is significant, and significant means it is a linear equation. It has been proved statistically that it is a linear relationship. So mean square due to linearity can be calculated, or mean square due to regression can be calculated. Sum of square due to regression divided by degrees of freedom, and mean square due to residual can be calculated by sum of square due to residual. Remember, here it is residual, and divided by degree of freedom. And then F calculated is MSL divided by MSR. And inference is compare the calculated value to the tabular F value at 1 and n minus 2 degree of freedom. The linear relationship is just to be significantly different if the value of it is greater than F table. F table at the prescribed level of significance. Otherwise, we look for higher degrees of freedom. So, any question up to now? Any question up to now?
Sorry, SSL means sum of square for linearity, no?
Pardon?
Sir, SSL means sum of square for linearity.
Yeah, or sum of square
Okay,
for
sir.
regression. Actually, there were two R. One was regression, other was residual. So therefore,
Yes, sir. Both are.
therefore I put it L. Otherwise, that is for regression. Now we start the second part. Can you see the presentation? Hello?
Yes, sir.
You can see it.
Yes, sir.
Now what we do, I just gave you a little bit of theoretical background. Now with the help of practical example, I will try to explain you each and everything so that you do not have any doubt about any aspect of this topic. So this is example. A field experiment was conducted by taking different levels of nitrogen in mustard to test its effect on seed yield. From the data given in table 5, fit a linear response equation and test it for linearity. So this is complete package to understand everything. Also plot the response curve from the computed equation and perform the correlation analysis. One advice to all of you that I have sent you Gomez and Gomez book, and there is one chapter on correlation regression analysis. All of you should read that chapter in your at least in your MSc program. So to make more clarity, more understanding, good knowledge of this subject is very, very important. You can read that chapter from page 1 to last page. It will give you sufficient idea, sufficient knowledge about this subject. So you will never ever have any doubt. So now you see this, I don't know whether you can see this table or not. Is it visible to everyone? This table?
Yes, sir.
Okay, is it very small? Because many of you use mobile. So now you see same data. It does not matter whether your crop is mustard or crop is wheat or rice. It really does not matter. And it does not. It also does not matter whether it is nitrogen or phosphorus or potash. You can have any fertilizer nutrient here on x-axis. And never say that. Never consider that it is just for nitrogen. We can decide the optimum dose. You can have any independent variable here. Even you can have fertilizer herbicide rates. Students who are interested in herbicides, they can have herbicide rates here. Rates of water application 5 liter, 20 liter or 30 liter likewise. So anything, any variable which has some values, some numerical values and increasing values can be written here as independent variable. And then dependent variable, mostly if you want to work out the economics or optimum dose of fertilizer, then you need to keep the yield of the economic part. So here, suppose grain yield, seed yield, tuber yield, fodder yield, whatever you have, you can put the yield here, the data related to yield of any crop. But otherwise, many times students like to see the relationship between any other dependent variable. Suppose you want to make the relationship between fertilizer application and nutrient uptake. So here you can put in place of Y, you can put nutrient uptake. How much is the nutrient uptake at different levels of fertilizer? What is the nutrient concentration? You can make the relationship between nutrient concentration and your nitrogen application, nutrient application. Similarly, you can take plant height here. So you can make any variable. If your interest is not in economics, then you can put any variable here in place of Y, which you consider I want to take it as dependent variable. Even you can take some soil parameters, the residual nitrogen in the soil after harvest of the crop. So you can take here. So it is really, it has very wide scope. This subject has very wide scope to have relationship between independent and dependent variable. Then I told you that we need to work out the value of A and B. If we want to calculate value of A and B, we need to calculate certain corrected sum of squares and total sum of square. So first one is that you need to take the mean of X and mean of Y. So mean of X is independent variable, summation X upon N. So you make the total of these all X, which is 240. And pair of observation are 4. You can see 0, 40, 80, 120. So 240 divided by 4, you get 60 as the mean of X. Similarly, you can work out the mean of Y, which is 19. So yield. Then you have a small x. It is deviation against the mean for independent variable or for X. So 0 minus 60, 40 minus 60. So you get value of a small x. Similarly, value of deviation against mean of Y. So yi.
Sir, please tell one second small x, sir. What is small x, sir?
Yeah, small x is your deviation against the mean. It is deviation against the mean. In your first column, you have x. You have x, this kg nitrogen per hectare. So x is your independent variable, which values are 0, 40, 80, 120. Y is your yield. Yield is in quintal per hectare. This Y. So you need to, for calculating value of A and B.
Sir, then sir, minus 60 into minus 0 minus minus 60 equal to minus 3600.
Just wait. I've not gone there. Just see it.
Okay, sir.
I'm telling you.
Okay, sir.
Yeah, I'm telling you. Don't worry. See, you are calculating the deviation against the mean. So in this column, small x within bracket xi minus x bar. So here xi means the pair. Which pair you are dealing with? Pair of ith pair of observation. So suppose it is first pair. First pair is 0, 17.2. So in this case, x is 0 and your mean of x is 60. So 0 minus 60. So therefore, small x is deviation. So actually,
सर
yeah.
सर x इजुगल टू होगा तो ज्यादा हम लोग समझने क्या बोलते हैं उसको अच्छा होता सर. x इजुगल टू होता तो मोर एप्रोप्रिएट.
X is good.
ये ऐसा लग रहा है ये मल्टीप्लाई हो रहा है. स्मॉल x मल्टीप्लाई ब्रैकेट में
Yes,
ये जो
sir.
है
Yes, sir.
Oh my God.
ये इजुगल टू होता
I
तो
think it is
अच्छा होता.
multiplied. That's why
no,
I
no.
asking, sir. It should be minus 3600, sir.
Okay. So actually,
That was doubt, sir.
you no problem. You are real mathematician, that means. So sometimes mathematics does not work. So to make you understand, I got it. So actually, this is you have taken it in mathematical sense. Yes, I will correct
Yes,
it.
sir. Now no problem, sir. We got it, sir.
I will correct it, but now I was not able to understand what you were asking. Now I am able to understand. Thank you very much. I like it. So actually, for the last I think 20 years, I think nobody pointed out. You are the first to point out. For last
सर
20
पहले
years,
तो ये ऐसा लग रहा था ये मल्टीप्लाई हो रहा है. देन 0 minus 60 then minus 60 आ रहा. ये समझा.
yeah, it is mathematically it is incorrect, and I'm thankful to you to find out this mistake. I was thinking that you are not able to understand this simple thing actually from my side, but mathematically it is wrong. I will correct it. I make a promise that I will correct the mistake which I could not do in 20 years, last 20 years. So no problem. I will correct it. But now you got me. You got me. So this x is equal to, definitely it has to be x is equal to. So xi minus x bar. So minus 6. Now you know, understand. Same way is small y is equal to yi minus y bar. And then you can calculate the mean of y. Mean of y is your 19. And then this 17.2 minus 19, and you can calculate a small y. And then x square. small x, you remember this can be squared. And similarly, xy, column number 3 and column number 4 can be multiplied to get xy. And similarly, y square, you got a small y, column number 4, square these value, you get a small y square. And then you make the total of all these columns to get their sums. So for example, summation x is 0, summation y is 0, because these deviations are against the mean. And then x square, small x square, make the total of this, which is 8,000. Summation x square, xy, summation xy is 224. And then y square is 6.38. So you can see here, summation x square is 8,000, summation y square is 6.38. The 6.38 is total sum of square. Now, summation xy, cross products, summation of cross products is 224. Now, this is the formula. This is the formula you need to remember. You must remember it. I may ask you in the examination, summation xy upon summation x square is equal to 224, 8,000. So you get the value of b as 0.028. 0.028. This is the value of b. Means if you make a unit change in x, this much of change is there in y. This much of change is there in y. So a is equal to y bar minus bx bar. So this is a relationship already known to us. So y bar is mean of y. So we can calculate the value of a by this relationship. A is equal to y bar minus bx bar. 19 minus, in place of b, you can put 0.028 into 60, and then 19 minus 1.68. So value of a is 17.32. Any issue up to now?
No, sir.
Okay. Now, the linear equation is y is equal to 17.32 plus 0.028x needs to be tested for linearity. Means whether it is linear or not. We have developed the equation, means this is the best fit equation. If you draw this equation, that will be the best fit. It will give you minimum values of the error sum of squares or residual sum of squares. So this equation needs to be tested for linearity, whether it is linear or not. Whether the two variables are really following a linear relationship or have some other kind of relationship. The analysis of variance, ANOVA, is performed and variation is partitioned into different components, that is regression or linearity or error and error. So F-test is used to test the significance. Sum of squares, mean squares, and total sum of squares are computed. You can see in the next table. The slope of the linear regression line may be positive, negative, or zero, depending on the relationship between y and x. The slope can be positive, it can be negative. So that is actually direction of change. So total sum of square in this case, if you remember, because this is 6.38. Sum of square due to linearity, because you got, I have shown you equation in the last part of the lecture. I have shown you the ANOVA table. In that ANOVA table, you need to calculate sum of square due to regression and sum of square due to residual or error. So sum of square due to linearity or regression, it can be calculated by summation y square is equal to summation xy whole square divided by summation x square. So you can put these values 224 whole square divided by 8,000. So you get 6.27 as sum of square due to regression. Sum of square due to regression is 6.28. And then sum of square due to error or sum of square due to residual r kept summation y square r is equal to total sum of square, that is summation y square minus sum of square due to regression. sum of square due to regression, just you calculated above 6.27. So, sorry, sum of square due to regression. So this is simply by difference method. From total sum of square, you subtract the sum of square due to linearity. So 6.38 is total sum of square minus the same thing you can put here, 224 divided by 8,000, you get 0.11. Any problem to anybody in understanding this? In calculating the sum of square due to regression, sum of square due to residual or error. If clear, then you can calculate the mean square due to regression, and you know respective sum of squares are divided by degrees of freedom. So sum of square due to linearity or regression divided by degree of freedom, that is 1. So in case of linear relationship, degree of freedom is 1 for regression. So this is your 6.27, and mean square due to residual or mean square due to error, sum of square due to residual divided by degree of freedom, you get 0.055. And now F calculated MS, mean square due to regression, divided by mean square due to residual, you get 114 as the value of F calculated. You can put these things in the answers. You can put your answers in here. Sources of variation, linear and residual and total. So you know total, there were 4 pairs of observations in this case. There were 4 pairs, 1, 2, 3, 4, 0, 40, 80, and 120. There were 4 pairs of observation. Therefore, you have total degree of freedom 4 minus 1 as 3, and for residual 3 minus 1. Then it is your 2 for residual, and linear or regression it is 1. Sum of squares you have calculated for regression, for residual and total. You can put the values, divide them by degrees of freedom, you get mean squares, and then F calculated. This mean square regression divided by mean square residual, you get F calculated. The table value at 5% is 18.51% at, I'm sorry, 18.51 at 5% level of significance, and 98.43 at 1% level of significance. So you can see it is more than both. If your F calculated is greater than table value at 5% as well as at 1% level of significant, that means your results are significant, your F test is significant, and your equation is genuinely a linear relationship. Means the data you are given in this example represents a linear relationship, that is all. So on comparing the calculated value table to the table value at 1 and 2 degrees of freedom, the linear relationship is found out to be highly significant because it is significant both at 1% and 5% level of significance. So now you need to plot the linear response curve. Now you have made the equation. You have made the equation, and you have also found that the equation is significant. Then you can plot it. Now, then you can represent this equation in the form of a curve or in the form of a line or graph. We call it graphical representation. So now you want to plot it. So plotting the linear response curve. Here, because the change or your regression coefficient is same, it is 1 across all the levels of input. Your delta y upon delta x is same with the addition of each level of input or each increase in input. So therefore, you can, if you just calculate the first value and the last value, means if you calculate the value of y when your x is 0 and value of y when your x is maximum. So just by having 2 data, only y0 and y max, you can plot the equation. So plotting means making the graph or representing your data on the chart. So using the estimated linear regression equation, y is equal to 17.32. This was the value of A, and 0.028 is the value of B, regression coefficient. So compute the estimated y values, one corresponding to the smallest x value and one corresponding to the largest x value. So you get x minimum, y minimum, x max, y max. So y minimum is equal to A plus B x minimum. This x minimum is 0. So then you can calculate y minimum, minimum 17.32 plus 0.028. In place of x, you can put 0. So it comes out to be 17.32. Means the estimated value. You got the equation. In this equation, if you put the value of x as 0, 0, then your estimated value of y will be 17.32. So this is what we are making prediction. So in this case, your this is 37, and similarly y max. So because your maximum level is 120, so in the equation y is equal to a plus bx, here it is y is equal to a plus 17.32 plus 0.028. Here you can put 120 in place of x. So you can get the estimated value of y when your level is maximum. Input level is maximum. So y max 17.32 plus 0.028. This is your equation. And in place of x, you can put 120. Therefore, you get 20.68. So now you have 4 values and you can plot this. So plot the 2 points y min, yx, y max, and y min and yx max. Means 0, 0, and 17.32, 120, and 20.68. And then you can join these 2 points and you get the plot of the equation. Plot of the equation. Other data point will automatically come on the line. They will automatically come on the line. So this is how linear response curve can be plotted. By any problem to anybody? No problem. So it can be plotted like this. Suppose this is a hypothetical example. So here you can see y is equal to 2x plus 1. So you can either write it as y is equal to 1 plus 2x or 2x plus 1. It does not make a difference. American people write like this, y is equal to 2x plus 1. But in India, we write first a and then bx. So it does not matter. It is the same. So hypothetical example to show you that it is the best fit, best linear fit. So all the data point, your line is passing through all the data points. This is perfect linear relationship. Perfect. Here your R square is 1. You will know later in the subsequent lectures what is meant by R square 1 when R square is 1. So today I am a bit tired. I think I do not have energy. I could not have breakfast. So I cannot speak more now. And time is also going to be over. So attend the class tomorrow at 9. But your questions are welcome.